Hello everyone, welcome back to our channel. Today we will continue our discussion on operators and we will also be taking a look at vector declaration in Verilog. So without further ado, let's begin. The first operator we are going to understand today are the shift operator. Verilog provides us with four kinds of shift operators: logical left shift operator, logical right shift operator, arithmetic left shift, and arithmetic right shift operator. So how do they work? Logical left shift operator shifts the bit towards the left by the specified amount of places provided. As you can look in the code, I have two registers A and B. A is signed to declare any variable. Signed or unsigned, you can use the keyword signed. And for unsigned, you don't need to declare anything. By default, each and every variable in Verilog is unsigned. Hence, we declare variable A as signed and we provide the value with minus 8 tick D8. Now what is this tick and D8? 8 specifies the width. How do we declare multi a variable with a width greater than 1 bit are known as vectors. And how do we work with vectors? We will be taking a look at it in this video itself. For now, you understand that A has been assigned this value. Okay. So what will logical left shift operator do? Logical left shift operator will simply shift this whole bits towards the left by 2, as we have mentioned 2 here. If I mention 1, then all the bits will be shifted left by 1. And on the right side, the zeros will be padded in the case of logical left shift. In the case of logical right shift, all the bits will be shifted towards the right. And zero padding will be done at the MSB side. Now, why do we need arithmetic left shift and how do you declare? Arithmetic left shift also behaves similar to logical left shift. It shifts the bits toward the left. But arithmetic, in the case of arithmetic right shift, you can see the difference. As in the case of signed numbers, logical right shift will not carry forward the MSB. I will repeat. In the case of signed numbers, logical right shift operation won't carry forward the MSB, but arithmetic right shift will carry forward the MSB. Let me show you here. How does that work? We had number A as 4 ones, 1 and triple zero. In the case of arithmetic left shift, what will happen? All the bits will be shifted towards the left by 2. As we can see, triple one zero zero, we have two zeros appended. And in the case of right shift, all the bits have been shifted towards the right by 2. But as the number is signed, in the case of arithmetic right shift, the, the bits that are being appended will be 1 as the number is signed. And if the number was unsigned, there won't be any difference between logical right shift and arithmetic right shift. I hope the shift operators are clear. These are very much useful in developing logic, as you all must be aware, to multiply any number by 2, we can just left shift it by 1. That number will be multiplied by 2. So this operator will help you in future whenever you need to perform multiplication or division of any number in the respect of power of 2. Now let's take a look at the conditional operator. It is commonly used for selecting between two values based on a condition, like an if-else, but in a single expression. Verilog provides us with the support of conditional operator, which can be used to select which output is to be assigned based on a given condition. Here we see I have a register A, I have provided value 5. A register B, the value provided it to is 10. And I have a register select that has been provided value 0. And I have a wire output. So as we have discussed earlier also, to provide value to any wire, it has to be continuous assignment. For this, we use assign keyword. Now we assign out is conditional operator. You might also hear it name as ternary operator. It is called both conditional operator or ternary operator. Now based on the value of select, if the value of select is true, then A will be provided as output. If the condition select is false, then B will be provided to out. So in this case, the value assigned to select is 0. Hence, out value will be A. As I mentioned earlier, if the value of select is 0, then out will be 10. And if the value of select is 1, out will be 5. It may seem simple right now, but conditional operator helps us to select between multiple outputs and which has to be assigned based on some condition. It's just like writing an if else, but not using if else state. Now, vector declaration. In Verilog, vectors are used to represent multi-bit buses, registers, or wires. In real life also, there are many registers or buses which are not single bit. So, to model all those, Verilog provides a support of vectors. The syntax of declaring any vector is, first of all, we need to specify the type of the data type of the variable we are trying to make vector, then MSB, that what will be the most significant bit size of that variable. Then LSB, from where, what is the least significant bit, and the name of the variable. The type can be wire, reg, etc. Name is the name of signal, and MSB to LSB. Let's take a look at some examples of vector declaration. I have a reg 7 down to 0. That means it is an 8-bit register from bit 7 to bit 0, and the data width, bit width is 8 bits. Be careful here, as beginners sometimes write 8 down to 0, but you have to count that if I write from 8 down to 0, then that would be 9 bits instead of 8, as we are starting from 0. So if I want a 8-bit register, I need to declare it as 7 down to 0. Similarly, I can also declare wire as a vector. Wire 15 down to 0 address. That means I have a 16-bit wire named address. Reg signed 3 down to 0 signed data. Also, as I mentioned earlier, by default, each and every data type in Verilog, to declare a variable as signed, after we declare data type and before we declare the width, we can use the signed keyword to make any data type signed. Hence, this is a signed data of 4-bit, where the MSB of this signed data will be used to see if the whole data is signed or unsigned. Now, the reg 0 down to 7. We can also declare it like this. Here, the MSB will be stored at bit 0, while the LSB will be stored at bit 7. Technically, it is possible to write like that, but we don't suggest this because the whole industry is aligned having MSB at the left side. So if you write like this, it will cause confusions for you as well as someone else who is trying to use your code. So technically it's possible, but it is not recommended to use reverse indexing. Now let's take a look at an example. Here also I am declaring a reg 7 down to 0 byte data and a wire 3 down to 0 nibble wire. I am assigning nibble wire equal to byte data 3 down to 0. What does this mean? This means I am assigning only the lower 4 bits of byte data to nibble wire. As byte data is of 8 bits, but nibble wire is only of 4 bits. So this is called part selection. I can select how many bits I want to assign to nibble wire. Now here, as I mentioned, if I had used reverse indexing while declaring the byte data, then I would have to use 4 down to 7 here to assign the lower 3 bits, which can cause some confusion. Hence, we recommend to use this ordering while declaring any vector. These are some key points to keep in mind while using vector declaration. Part selection, as I mentioned, must be in the same direction as a declaration direction. If I declare a vector as 7 down to 0, then I can part select the data as 7 down to 4, but not as 4 down to 7. Size mismatch can cause truncating or padding. If here I had not explicitly mentioned 3 down to 0, then also Verilog will automatically truncate the upper 4 bits and only assign the lower 4 bits of byte data to nibble wire. Hence, when assigning one variable to another variable, make sure their sizes are equal. If their sizes are not equal, then padding or truncation can take place. If we are assigning a wider vector to a narrower one, it will Verilog will truncate the upper bits. Assigning a narrower, that is a 4-bit, a smaller variable to a larger variable, the extra bits which are not present, they will be filled by zeros. Or sign extension can take place if the smaller variable is signed. Now, indexing starts from MSB to LSB unless declared otherwise. That is, bit 7 is the MSB and bit 0 is the LSB. Also, by default, all the vectors are unsigned. To declare them as signed, we need to explicitly declare them as signed variable. As we understood the example, signed operations perform differently compared to unsigned, especially in case of shift and comparison. Now, last but not the least are concatenation and replication operator. This is, I feel, one of the most simplest operator present in Verilog, but it has very huge use case while developing your each and every program. The operator is concatenation operator. The role of the concatenation operator is simply to combine multiple values or signal into a single vector. What do I mean by that? Let's take a look. We have two registers A and B. Both are 4-bit each. The values provided to them is 1010 and 0101. I have another register C. Now I can directly assign value of A and B to C by combining them. That uh, concatenation A, comma B. That is, C will be assigned as 10100101. A will be stored in the upper 4 bits of C, while B will be stored in the lower 4 bits of C. This is the concatenation operator. Now we also replication operator. That is, this repeats a value n time and concatenates the result. I have a register A which is of 2 bit. The value of register A is 1, 0. Now I assign B is equal to 3 replication of A. This is the syntax of replication operator, where 3 signifies how many times I want to replicate the value of A and then assign it to B. So A was 1, 0. Now I replicated 3 times. Then what does it become? 1, 0, 1, 0, 1, 0. And finally, this is concatenated and assigned to variable B. This is how replication operator works. These both operators may look simple and are all they are actually simple, but you need to figure out there are many use cases where they will be so helpful to you. There's some key things to keep in mind while using both of these operators. The concatenation is left to right, that is, A goes to the higher bit and B goes to the lower bit. Each item in concatenation operator must have a known width, or it can cause size measure. Here, if I do 4 times replication away, what will happen? At the RHS, I will have 8 bit data. But on LHS, I only have 6-bit width. So, as we discussed earlier, if I have more bit data on RHS and less width on LHS, then the upper bits will be truncated. The same will take place here. So, to properly assign, we should have a known width. Replication is equivalent to repeating and concatenating the same vector. We can also combine both replication and concatenation. That is, repeat twice of A, then concatenate with B, then assign it to something. This is very useful in test benches when we need to generate values like this. So rather than manually typing 8 tick B111, that is typing 8 times 1, we can simply use replication operator. I hope all of this is clear. If you have any doubts, please feel free to drop them in comments. We will be happy to help you. Thank you for watching.